why do you think it is, maybe best practically speaking, these are my words, not yours, to treat the unification of gravity and quantum mechanics, on the other hand, as a low energy versus a high energy problem?
I'm sorry, you already asked, and I forgot to comment on that. So, yeah, just for context, I should say, so usually people who are interested in quantum gravity have been traditionally considered to be part of the high energy physics community. And, that's great because there are a lot of really amazing physicists, and we get to say that there are colleagues who do high energy physics. But over time, so why did people think that way? Well, if you think like a high energy physicist, what you're thinking about is higher energies allow you to probe shorter distance scales. And that's why we build these big accelerators, so we can accelerate particles to higher energies. That effectively makes a better microscope. You get to see what's happening at shorter distance scales. The relation is inverse, so the distance scale you can probe is sort of inversely related to the energy you can get these particles to. That just comes out of the structure of quantum mechanics. It's the way quantum mechanics works. In that sort of mindset, you can ask, well, at which point is gravity even going to matter for me? Because, if you're a high energy physicist, gravity usually doesn't matter at all. Gravity matters for large objects where a lot of mass can sort of accumulate, and then the masses can tug on each other. Gravity is in a sense a very weak force, in that if you ask, let's say for a hydrogen atom, what holds the proton and the electron together, there's an electric force that holds them together. It's many, 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 many times greater than the gravitational attraction between them. Okay. But of course, gravity will become important eventually when you concentrate a lot of energy in a small region. Then maybe you can make a black hole. And so you can ask, well, how big does the energy at an accelerator have to be so that you probe that kind of distance? And the answer is, like a billion times higher than any energies or something like that we currently probe accelerate, enormously higher. Okay, so in that sense, quantum gravity is a high energy problem, that if you crank up the energy in particle collisions by such a ridiculous factor, then eventually you're going to make tiny little black holes instead of new particles. Now, that is true. I don't doubt it. But it's not been a very fruitful way of making progress in quantum gravity. What has been much more fruitful is the kind of direction that began with Bekenstein's and Hawking's work in the 70s, where we ask, well, what do black holes do? Black holes do interesting things that have become more interesting when they get bigger, because we have better control over the arguments. The fact that black holes radiate, that they seem to lose information and so on. The argument for that gets better when you consider bigger black holes than smaller ones, because the sort of corrections due to unknown quantum gravity theory effects become smaller, should become smaller, we think, in that limit. Then we learn about the holographic principle. We learn that gravity knows about its own quantum states, that it knows about the quantum states of matter. Things like my own discoveries, the covariant entropy bound and so on, teach us that there's a connection between geometry and information that's very universal and in some sense becomes more powerful at large distances than at small ones. If I tell you that the amount of information in some region of space is controlled by the area of the surface and not by the volume, one thing I've told you is that it's also much smaller than you might have thought. Normally we think that we can sort of put independent bits of information in each little cell of volume, and so the information should grow like the volume. In fact, I can only put as many zeros and ones as there are tiles that fit on the walls of the room. That's a lot less zeros and ones. And that discrepancy between how much information we naively might have thought is in the world and how much there really is in the world, that discrepancy becomes more and more drastic the bigger the regions are that we consider. So in that sense, I think most of the really interesting things we've learned about quantum gravity pertain to large distances. They become sharpest and most dramatic at large distances. They have nothing to do with trying to go to very high energies. And so it's in that sense that I think we're not studying a high energy problem. That's not where the key difficulty and the key and the fun is with the problem.